No. Okay, chapter 4, let's do this thing. Hopefully the beginning of this video will be boring and kind of easy because I'm sure you've seen basics of power equations before. That might be a new name for you. You might not have heard the phrase power equations before, but I'm sure you know about them. A quadratic is just one particular example that we'll look at in general here. But be sure to check the end of the video for technology advice. Not everybody starting this course is a calculator whiz right away at the beginning, but I want you to be. So please make sure to watch through to the end. All right, so section A, power equations, just an equation in this form. Okay, so x squared equals a constant. That's a power equation that happens to be a quadratic equation. X cubed equals a constant. That's a power equation that just happens to be a cubic equation. So power equation is just a general name for any equation that are in that form. And we know that when the power, which in this case is n, obviously can't be 0, right? Because then I would have something to the power of 0, which we know would be equal to 1, as long as that something isn't 0. What was I saying? Right, so if that power is even, then we're going to have generally two answers to it, plus or minus the nth root of our constant, as long as that constant's positive. But we could have only one solution if the constant was 0, because plus and minus 0 is the same thing. And we're going to have no solutions if that constant's negative. We can't have a real solution for x squared equals a negative or x to the fourth equals a negative and so on. So that's our rules for even powers. And if it happens to be an odd power, then we don't care whether k is positive, negative, or 0. We're always going to have just one answer, and it'll be the nth root of k. So these three should be very straightforward. The cubed root of negative 27 is going to be negative 3. Letter B, we're going to move the 5 over, giving us x to the fourth equals 10. And then the answer is just going to be the fourth root of 10, plus or minus, of course. So there's going to be two answers to that one. And then this third one over here, we move the 5 over, getting 6. When we divide by negative 2, however, we get x squared equals negative 3, and that's going to have no real solutions. We can also use this thought process for when we have a binomial that is being squared. So like, yeah, I know about quadratics, so I know that I could expand this thing to get x squared plus 6x plus 9 equals 36. And then move the 36 over and use some quadratic formula stuff. We're going to talk about that in a minute. But you could also just take the square root of both sides, and then that's very easy. So we have plus or minus 6, and then we're going to subtract the 3 from plus 6 and from minus 6, so we'll get two answers at the end. And then certainly you don't want to use the expansion technique for the second one. I mean, x minus 2 to the power of 5, yeah, I can expand that, and we will be working with binomial expansion later on in this course, but that's a huge hassle. So instead, let's just take the fifth root of 11 and then add 2 to it. And we can do the same thing for like negative exponents as well. We're just going to, basically flip over the other side of the equation, all right? So that's how the book explains this. I would probably mentally take the first line and then raise both sides to the negative 1/5 power, because then on the left-hand side, negative 5 times negative 1/5 are going to cancel out, leaving us with just x. And then that's going to be equal to, well, on the right-hand side now, we can apply that negative exponent there, and so that'll give us just negative 32 to the negative 5th, to the 1/5. And then I know that I'm looking for the fifth root of negative 32, which is negative 2. But I mean, whatever. Obviously, they did the same thing that I did. Okay, moving to section B, we know that when we have a product of numbers and the answer is 0, then at least one of the factors being multiplied together must have been 0. And it's true when there are two things being multiplied together, but it's also true when there's 3 or more. So in our first example down below, we've got a product, it's equal to 0. So that means either 3 is equal to 0, but of course it's not, or x is equal to 0, so that's one answer, or x minus 5 is equal to 0, which of course means that x is equal to 5. On the right, we've got two factors here, so either x minus 4 is equal to 0, so x is 4, or 3x plus 7 is 0, so x is equal to negative 7/3. All right, so one type of power equation is a quadratic equation. Let's talk about them more generally now. This is their standard form. Ax squared plus bx plus c is equal to 0, where a, b, and c are constants. And of course, a is not 0, otherwise it would have been linear. A quadratic equation can have two solutions, one solution, or 0 solutions. And in order to find those solutions, we will use one of 4 techniques. If the quadratic seems easy, then I recommend factoring it and then setting each of those factors equal to 0. If it seems a little more complicated, then it's kind of your choice. You can either use completing the square or the quadratic formula. People tend, in my experience, to really like one or the other. I'm a quadratic formula guy, but maybe you like completing the square. Now, the truth is there's no quadratic out there that you shouldn't be able to work out by hand. However, we're going to talk about using technology in this video just to preview it, because later on in the course, when we have more complicated types of equations, we're going to need to know how to use it. Factoring. Here are your steps. Down below, we got 2 examples. I don't really have anything to add to them because you should know how to factor a quadratic at this point in your mathematical career. Be sure to know your shortcuts as well. So like here we have an example of a minus b squared. And we also need to know a plus b squared and a plus b times a minus b, the difference of 2 squareds. Now, one thing we got to really be on the lookout for factoring is actually factoring instead of doing something else that's stupid. And what I mean by that is, of course, dividing by 0 accidentally. People do this, all right? People make this mistake, so don't be too hard on yourself if you catch yourself doing this at some point. If we have x squared equals 5x, you might be tempted to do this wrong thing right here and divide both sides by x, and then you get an answer, and you get x equals 5, which is one of the answers, but it's not the only one, because we might be dividing by 0. Right there, we divided by x, but we don't know what x is, so x could be 0. And in fact, that was one of the other solutions. So the correct solution over here has x equals 0 as one of the answers. So when we divide by x, or when we divide by an expression with a variable, that can happen sometimes. And we have the same thing can happen when we take the square roots of both sides of an equation. Over here on the right, again, we have a wrong answer. So we see that they're just taking the square root of both the left-hand side and the right-hand side, so they just get rid of the parentheses and the squares, and then they solve and they get x equals 8, which is one of the correct answers, but it's not the only one. We're missing the 2. So the book suggests that we use factoring. This is a little bit tougher to see what's happening over here. So let's take a look at it. First, obviously, they subtract the x plus 1 squared over to the other side. And then what we have is a squared minus b squared. So the shortcut that I just referenced. That's why in the next step we have 2x minus 7 plus x plus 1, and then 2x minus 7 minus quantity x plus 1. And then you simplify both of those, and then you get 2 factors, and then clearly we have x equals 2 or x equals 8. Now look, there's lots of other ways you could do this. You could expand both 2x minus 7 squared and x plus 1 squared, and then combine all the like terms on one side of the equation. That's absolutely going to work out just fine. And we could also employ this little tip right here. If a squared equals b squared, then a is equal to plus or minus b, meaning that in addition to 2x minus 7 equals x plus 1, we should also be solving 2x minus 7 equals minus x minus 1. Because if we solve that one, we end up with the solution x equals 2. The point of all this is don't just go dividing both sides of an equation by a variable or an expression with a variable, and don't just go around taking even roots of equations on both sides all willy-nilly, because you might end up missing a solution. All right. completing the square. Again, here's the steps for it. I don't really have anything to add, so just jot them down and then we'll look at an example together. So this has got everything that a completing the square problem could possibly have in it. So the first thing we want to do is change it from negative 3x squared blah 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 to just 1x squared blah blah blah. So we're going to divide everything by the negative 3. And then we're going to move the constant over to the other side. And then we're going to take half of this b term, so that's going to be negative 2, and we're going to square that to get positive 4, and we're going to add that to both sides. And what we have done without fail at this stage is we will have made a perfect square trinomial right there. That happens absolutely 100% of the time. And the perfect square trinomial can be factored into x, and then it's always going to be half of that term right there, quantity squared. And then that's all equal to whatever we had on the right-hand side, which they've combined some like terms for here. Great. And then if we want to solve this thing, well, now we can just take the square root of both sides and then move the 2 over. Completing the square is also helpful for a few other mathematical things. Just off the top of my head, certainly writing a quadratic in vertex form. We'll cover that later on in this course. And then helpful perhaps on the SATs, although it's not a part of this course officially, is writing a circle in center radius form. So completing the square is definitely helpful in some contexts. I just don't happen to use it for solving quadratic equations. I prefer the quadratic formula. So there it is in all of its glory. I think you should just have this thing memorized. You're going to end up using it often enough. There's songs and stuff out there to help you if you need that. I'm certainly not going to sing them for you. I will, however, share this mnemonic device that may help you memorize it. It goes a little something like this. Look in the formula book on page 5, SL 2.7. There you go. All right, down below, I don't share a lot of proofs in this video series, but this one's pretty simple and it connects completing the square with the quadratic formula. So if you accept that completing the square is a valid way to solve a quadratic, then using completing the square, we can derive the quadratic formula from this general equation. So I don't know, that's kind of neat. Take a look at it. Now let's use this formula. Okay, so anytime we've got a quadratic equation, we need to figure out what the values for a and b and c are. And there's our answers. So very often we're going to have answers that are going to have surds in them. Okay, great. Solving quadratic equations by hand, those are the 3 methods. And we'll hit technology in just a minute, but I got to add one other really important thing about a quadratic now, which is the discriminant. And a lot of American mathematics courses tend to overlook this thing, but the IB loves it, so we got to make sure that we know the discriminant. All right, we're going to use the symbol here. Greek letter delta represents it, and the discriminant is just the thing that was underneath the square root. And what do we need to know? Well, obviously, if that thing underneath the square root is a positive number, then we're going to get 2 solutions, 2 different, distinct solutions from our quadratic equation. One where it's plus the square root of that number, and one where it's minus. We saw this on the previous slide. If the discriminant happens to be 0, well then there's only going to be one solution, because we're going to be getting plus 0 or minus 0. If the discriminant's negative, then we're going to have no solutions because we can't take the square root of a negative. In the case of 0, this is important, we're going to call that, even though there's only one solution, we're going to call it a repeated solution or a repeated root. That becomes really crucial later on in the course when we start looking at polynomial or equations more generally. There must be the same number of solutions or roots as the highest degree in the equation, but that's after we start talking about complex numbers, that becomes really important. So anyway, yeah, so discriminant positive, 2 distinct real roots. Discriminant 0, 1 repeated real root, and discriminant negative no real roots. And of course, if the discriminant's a perfect square, then the two roots are going to be rational because we can take the square root of the perfect square, but whatever, that's not the interesting thing about this. So this is boring. Just use the discriminant to determine the nature of the roots. All right, so in each case we figure out what b squared minus 4ac is. In the first example, it's negative. In the second example, it's positive. So that means negative discriminant, no real roots. Positive discriminant, two distinct roots. 40 is not a perfect square, so that means that my two distinct roots are going to be irrational. Now, when I first learned a discriminant, that's kind of where we stopped, and I thought it was kind of dumb because I was like, hey, you know, I could just solve these equations, and maybe that would take me a few seconds longer, but I would still know about the roots, and then I don't need to try to like memorize that stuff on the previous page. Okay, that's true, but the IB does quite a bit more with the discriminant, because what if we don't know the value of A or B or C? So in this case, we want to figure out, you know, what values would M have to be to give us each of these three cases. So the first step is going to be to figure out what the discriminant is. So in our case, it's 4 minus 4m. Now 4 minus 4m could itself be positive, or it could be 0, or it could be negative. So for each of those two inequalities and one equation, we're going to solve for m. And we see that when m is equal to 1, this quadratic does have one repeated root. When it is anything less than 1, then there's always going to be two roots. And when it's anything bigger than 1, there's going to be no real roots. I also won't include it here because we'll see examples in class, but it's possible for the discriminant itself to be a quadratic. So if that m had been part of the b term, for example. And then we just need to work a little bit harder to, I wouldn't say it's anything special, but it is something that the IB tends to ask about. All right, while we're talking about roots, let's talk about their sum and product. So this is really important. In a quadratic, if we know that its two roots happen to be, we'll call them alpha and beta, then the sum of alpha and beta is going to be equal to negative b over a, and the product of alpha and beta is going to be c over a. And again, we have a proof down below if you're interested in that sort of thing. These formulas are not in the formula book in this form. However, there is a more general formula available also at the bottom of page 5, HL 2.12, that can be applied to any type of polynomial equation, so quadratics, cubics, quartics, etc. But we'll tackle that formula when we get up to that stuff. For now, I think you can just memorize negative b over a and c over a. Now the way that we end up applying the sum and product of the roots to quadratic equations can be a little weird, so let's take a look at one. So we start off by being given a quadratic equation, and we could solve that, get those two roots, but sometimes that's difficult to do or annoying, and there ends up being a potentially faster way. And B, sometimes the instructions from the IB actually say, without solving the original equation, find this other new one, which at first glance, like how you know, you want me to not solve this one, so operating completely in the dark, I don't even know what the roots are, how could I ever find out this other equation? Well, there's two ways. One way is to cheat and secretly solve the equation on a piece of scrap paper, and then that's not going to get graded, and then try to like get something going on working backwards from there. I really don't recommend doing it that way. What I recommend is doing the following. So we look in the original equation and we say, well, I don't know what alpha and beta are, but I can work out what their sum and product are. So let's do that. So the sum is going to be negative 5/4, the product is going to be negative 1/4. And now I'm going to use this and this to figure out something about not alpha and beta, but 3 alpha and 3 beta. And we can see that by just some simple factoring, we can work out what the sum and the product for our new equation need to be. Conveniently, notice that the denominator of both of these happens to be the same thing. That's always going to be the case because when we took the sum and the roots of the original, it's always going to be divided by the original a term. And anyway, we're going to exploit that now to rewrite our new equation because it's going to have that same a value. So there we have it. The numerators tell us our b and our c value, and the denominator tells us our a. So there we go. Now this particular question said find a quadratic equation with roots 3 alpha and 3 beta. We just found a quadratic equation with those roots. It's not the only one. If the problem had said find all quadratic equations, then the work would have been identical, except at the very end, we're going to do what our little friend is saying here. We're going to add a constant scalar to the entire quadratic. So we're going to multiply 4x squared plus 15x minus 9 by k, where k is some real number that's not 0. Because everything in this form is going to have the roots 3 alpha and 3 beta. It's just going to be a quadratic that's being vertically stretched somehow. All right, so section D, we're getting into technology now. Everything on this page I've already really said out loud earlier in this video. Polynomial equations contain our quadratics, our cubics, our quartics. Quintics would be something with x to the 5th. I forget the name for anything bigger than that. Really, above a quartic equation, we usually just say a 5th degree polynomial equation, a 6th degree polynomial equation, etc., where the degree is the highest power in the x that we see, and that number, that degree, is going to match how many how many total solutions there are, including complex solutions. But again, we'll discuss that another day. So for now, we'll just say if it's degree 7, then it could have as many as 7 real solutions, or as few as, obviously, 0. So anyway, let's take a look at a few polynomial equations and how we could use technology to solve them. Because generally speaking, once we get past the quadratic, we don't want to do these by hand. I mean, in fact, here, this is the cubic formula if you want to solve a cubic equation by hand. You don't want to do this. You want to use technology, okay? So here, let's do this one over here. I'm not going to do the quadratic. That's boring. Let's do this cubic on the right. So if we want to solve this using technology, first taking a look at Desmos, if we just type in the equation as given, it's going to give us 3 vertical lines. And each of those vertical lines represents one of the real solutions. So you can kind of tell, because it's easy in this case, that the 3 solutions are going to be -3, -2, and +1. But even if I click, I can't get those to show up. So if they had been decimals, like if this is -2.00000, you get the idea, I won't actually know that for sure from this screen. So what's better to do is move the 6 and the -x over to the left-hand side, and then make just a polynomial out of this, set it equal to y, and then we can find easily the 3 zeros on the screen. And this is pretty much what I'm going to show you on the TI as well. But Desmos is nicer, and I think you should be using it at home. By the way, remember these coefficients, 1, 4, 1, -6. We'll use that in a second. On the TI, if we're going to do a graph, we don't have the opportunity to graph the equation as it originally was. So one thing we can do is we can set our first function equal to the left-hand side of the equation and set the second function to the right-hand side of the equation, and it'll just graph both of those, and then we're just going to find out where they intersect. I can see one intersection on screen. To see the others, I would have to either zoom out or change my window, which we can do either by grabbing or by going to menu and then changing the window settings. Anyway, now I've got 3 solutions. I'll just find one of them. I press menu, analyze graph, and I want to find an intersection. Let's find this one right here. So lower bound means I'm going to put this line anywhere to the left of the solution I'm interested in. I press enter, it now says upper bound. I now move it to the right, and an intersection pops up. I'm only interested in the x value here, the y value is meaningless, so x equals 1 is one of the solutions. If we use the polynomial we saw before, so there's 1, 4, 1, negative 6 again, and then graph that. Now we're looking for the 3 zeros. So we go menu, analyze graph, find a 0. Same idea, lower bound, I'll click here, upper bound, let's say I want to find that one. Again, the x value is what I care about. Obviously, if I'm finding a 0, then the y value is 0. So whatever. Okay, so that's how to do this graphically. But we can do it on the main calculator screen as well. Here's how I don't want you to do it. There's this thing called nsolve, which you can get by pressing menu, algebra, and then it's the very first thing. If you then type in the equation as it was written, and then finish with comma x, that's your way of telling the calculator that x is a variable that you want to solve for. You press enter, it'll give you an answer, but it only gives you one of the answers. There's going to be more. So I'm not even sure why this functionality is left in the calculator. The CAS model has something called solve rather than nsolve, which gives you all of the solutions. That's helpful. Nsolve, this is only a good thing to use if you know there's only one. So pretty much never use nsolve, okay? You just use the graph or use this other thing I'm going to show you, which is menu, algebra, skip nsolve, go to polynomial tools, and then find the roots of the polynomial. The polynomial we're trying to solve is of degree 3. We could work out complex roots, but for right now we'll just deal with real ones. After all 3 of the roots in this example are real. And now it needs the polynomial to be in standard form, and we're going to enter in the coefficients of the x cubed, x squared, etc. terms. So those coefficients were 1, 4, 1, and negative 6. Okay, so a sub 3 is just the coefficient of x cubed, a sub 2 is the coefficient of x squared, and so on. A sub 0 is the constant. Anyway, we press enter, and then it's already filled it in here with the comma x. For nsolve, you need to type it. For polyroots, it's automatic. Press enter, there you go. Section E has nothing else in it except to say, hey, by the way, you can use the calculator for other equations that are actually not polynomial. So these two examples are clearly not polynomial. The first one has a 2 to the x, so that's an exponential on the left-hand side, but then it's a linear on the right-hand side, so that's not a polynomial equation. And then this one starts to look off like a quadratic there, but then we're dividing by x, and so that's not polynomial either. I won't go through the process, but in case you want to check your answers, they're on screen now. The bluish one was the first example. It has 2 solutions, and the reddish one was the second example. It has only 1 solution, although I could have, by adding a constant, made it have more than 1. I could have made it have, say, like 3. There you go. But anyway, that's it for section E. So now I just want to mention that technology, even though it's great, it does have limitations. And for an example of that, I encourage you to think about, first of all, solving this equation, x to the power of x equals negative 1. It's a little tricky to do algebraically. I don't know what it would mean to say that x is equal to the xth root of negative 1. I also don't know what it would mean to say log base x of negative 1 is equal to x. So the algebra is messy. If I graph x to the power of x on Desmos, it certainly doesn't look like it ever equals negative 1. If I set it equal to negative 1, it's not giving me any number. Maybe it's off screen. No. Oh, there's even a note here from Desmos telling me that there's going to be some sort of a problem. It says learn more. It says it's too complicated. What if I were to move the 1 over, plus 1, set it equal to y? No, that's not getting me anything because I want to figure out where this is equal to 0, and this is not touching the the x-axis. Jump to the n-spire. Maybe n-solve will give me something for this. Overflow, okay, that's not a good thing. And polynomial won't work, polynomial roots, because this is not polynomial. Let's try graphing it here. It's probably going to give me the same thing as Desmos. Or is it? Whoa! So that's interesting. Now remember that Desmos said that it was complicated, and it is. Desmos decided just not to show any x values that were negative, whereas the calculator is showing that something's happening there. Well, let's think about this. Obviously, some negative numbers we can certainly put into the expression x to the x, and it'll work. -3, for example. That works out just fine. But we couldn't do, for example, say -1/2 to the -1/2, because this is going to ask us to find the square root of a negative. And that's not possible, at least not within the real numbers. So that's why Desmos said, like, no, I'm not showing you anything over there, and the TI is giving us all this weirdness. So back to our original question, what's the answer to this? Well, just think about it for a second. Maybe you've already come up with this. X equals -1 is certainly a real solution to that. This is called solving the equation by inspection. It means just kind of looking at it for a minute until you realize, oh yeah, this simple answer does work for it. Cool, I got it. And sometimes, we'll see this later on when we get further into polynomials, sometimes the first step ends up being just by inspection. And of course, anytime we do that, it's going to be an integer, and it'll be an obvious, simple number. But it's worth being able to just have a little number sense to experiment with some things in your head. Because technology is, as evidenced here, not always going to do the job. In fact, some might say, and indeed someone has said, although the web search for this quotation will turn it up as anonymous, the human mind has never invented a labor-saving machine equal to algebra. Except for the CAS.